Hi guys, in this lecture we are going to learn how to create mathematical models of mechanical systems. So first of all, what is a mechanical system? A mechanical system transforms energy or power into forces and movements in order to accomplish specific tasks. A good example of a mechanical system is a windmill. It takes power or energy from the wind and converts it into rotary motion. Mechanical systems are best analyzed by using specific mathematical expressions for each of their core components. Usually, viscous dampers, springs, and lumped masses are sufficient. So I am sure that you're all familiar with springs. They compress or extend when you apply forces onto them. The mathematical expression for the force created by a spring is force with respect to time equals k, the spring constant, multiplied by x with respect to time, which is the compression or extension of the extremity of the spring which has been applied a force upon. So the force is proportional to both the spring constant and the compression or extension of the spring. What's interesting is that the spring constant is a constant because it is a given. It is decided when the spring is manufactured and completely depends upon its natural mechanical properties. So with the spring constant of any spring, you can calculate the force that spring generates when it is compressed or extended by a certain amount. Let's now look at viscous dampers or dashpots. So unlike springs which create a force proportionately to a displacement, dampers create a force proportionately to a velocity, which is the derivative of a displacement. So the mathematical expression for a damper is force with respect to time equals c, the damping coefficient, multiplied by the velocity with respect to time. The velocity is the velocity of the plunger, so the velocity of the extremity of the damper and how fast the chamber inside of it is moving. So here we can see that the force created by the damper is directly proportional to the velocity of its plunger, and it's proportional with respect to the damping coefficient. So the damping coefficient, like for the spring and the spring constant, is a given value with a damper, and it depends on the way that damper was built. The type of damping, which is expressed by the expression Ft equals C Vt, is called viscous damping, and it's widely used as an idealized model for damping in many engineering systems. This means that any kind of damping, almost any kind of damping, can be modeled using this equation of the viscous damper. It's very general and applies to many different models of damping. Finally, let's look at the lumped mass. So we know from the second law of Newton that the acceleration of a mass is proportional to the force applied to that mass. So here you can see from that diagram we have a mass m with a force Ft applied to that mass m, and it creates a velocity v of that mass moving in the same direction as that force, and a displacement xt also moving in the same direction. So we can express mathematically the situation with the following equation. Force with respect to time equals mass multiplied by the derivative of the velocity or the second derivative of the displacement, meaning the acceleration of the mass with respect to time. So Ft equals m multiplied by the second derivative of displacement with respect to time. Again, the second derivative of the displacement is the acceleration, simply because the derivative of a displacement is a velocity, and the derivative of a velocity is an acceleration. In order to understand how to apply these equations, let's look at an example of a mass spring damper system. This system that you can see in the diagram is free to move in only one translational direction, the direction x. And this is called a single degree of freedom system because it can only move in one direction. If no force is applied to the mass, then the system is said to be at rest, which corresponds to x equals 0. This means that there is no energy inputted in the system, nothing is moving, nothing is happening. It is at rest. However, here we apply a force to the mass such that the mass moves to the right in the direction x. Okay guys, so when you want to create the mathematical model of a specific system, it is very useful to represent that system using a free body diagram. Here we have the mass, represented as a big purple square. Acting and pulling on it towards the right, the same direction as x, we have the force, P. Reacting to that force, we have the forces created by the spring, Fk, and the forces created by the damper, Fc. And these are going in the opposite direction as the force Fp. So, using Newton's second law for the lump mass, we can write the equation of motion of the system. We know that all the forces are Fp acting towards the right, so in the same direction as x, so it is a positive sign, minus Fk minus Fc because these two forces are acting in the opposite direction of Fp. And this is the sum of forces acting on the mass. So using the second law of Newton and the equation that we saw previously, we can write that Fp minus Fk minus Fc equals m multiplied by the second derivative of the displacement x with respect to time, or the acceleration of the mass. Using the equations previously described, we can write that Fp minus k, the spring constant, multiplied by the displacement x of the mass, minus c, the damping coefficient, multiplied by the velocity of the mass, is equal to the mass multiplied by its acceleration. So the force can now be worked out as equal to the mass multiplied by the acceleration with respect to time of the mass plus the damping coefficient multiplied by the velocity of the mass with respect to time plus the spring constant multiplied by the displacement of the mass with respect to time. So this is the mathematical model of the mass spring damper system presented above. And what you can observe is that we have three terms, each a different derivative of x. So a second order derivative followed by a first order derivative followed by x. This is a second order differential equation, modeling the system of the mass spring damper. Rotational systems work in exactly the same way with different variables. So here, instead of a linear spring, we have a rotational spring Kr, followed by a rotational damper with a damping coefficient Cr, followed by a mass with inertia J, and instead of a force, we have a torque Tr. So exactly like before, we can use the second law of Newton to write the sum of forces acting on the mass with inertia J and equate it to J multiplied by the second derivative of the angular displacement theta. So the angular displacement theta means that the mass was turned by a certain angle. If you take the first derivative of that angular displacement, you will get the speed at which the mass has turned, and if you derivate that again, you will get the acceleration at which the mass has been turned. Okay, and developing these equations using the same formulas as previously, but just converting them to work with a rotational system. So you have the rotational spring constant multiplied by the angular displacement theta, and the rotational damping coefficient multiplied by the angular velocity with the first derivative of theta. You put them together, do the sum of forces with respect to the signs we saw before. So the torque will act in the opposite directions as the spring and damping forces. And finally, you have the mathematical expression for this rotational mass spring damping model. TR equals J multiplied by the second derivative of the angular displacement theta plus the damping coefficient in the rotational direction multiplied by the first derivative of the angular displacement theta plus the rotational spring constant multiplied by the angular displacement theta. So again, this is a second order differential equation in the rotational direction. This concludes the lecture on mechanical systems mathematical models. I hope you liked it. If you have any questions, please do not hesitate to ask me. It's very important and I'll be very happy to help you understand anything you need.